Now we move on to the next topic, which is power quality. So we can break this up into continuity of service, keeping the magnitude of voltages constant, and also how we can get sinusoidal waveform out of these 2-hour load here. All right, so let's, the most serious problem with power quality is discontinuity of service. Okay, so if you have some kind of critical load, some medical or computer equipment that must operate even if this utility voltage here were to get disconnected, there's a hiccup in the utility supply, we still want to keep on supplying this critical load. To do that, what we do is use so-called uninterruptible power supplies, UPS. And here we have energy storage. This maybe in terms of chemical batteries. And there's talk of using flywheels as inertial energy storage mechanism. So what we do here is that from the utility we rectify and charge up these batteries over here, start keeping our discussion to batteries for now. And then also this DC voltage here is inverted using that switch mode type principle that I talked about earlier to create back to 60 hertz over here. So we started with 60 hertz, let's say here, we get back to 60 hertz, same amplitude as we would normally have with the utility, and of course we are chopping it up at high frequencies, so we need a filter here. So that's shown as an explicit box over here. And then we apply this, whatever is coming from this filter to this critical load over here. So if utility were to disappear, so this block is no longer here operating, let's say, then energy stored in this battery here is providing the DC link, and the power is then flowing from here to this load. Otherwise, it's flowing from the utility to this load over here. So, and also some of it keeps this battery charged here. So that's the basic mechanism on which these uninterruptible power supplies work. For large industrial loads, there's a possibility of using 2 feeders. This feeder may be coming from a system which is somewhat remote from what is feeding this second feeder. So normally this load is supplied by feeder 1. But if there's a problem on this system here, we can switch it to the feeder 2 over here. Okay. So for large industrial loads, it is a possible option. And there's a great deal of emphasis on so-called hot transfer. So if the feeder 1 is disconnected and the load is switched to feeder 2, even though this load may consist of motor loads which are rotating, how can we transfer it from one feeder to another without any disruption? So that is called hot transfer. Okay, so these switches are made up of thyristors or IGBTs, and there has to be a great deal of intelligence in terms of transferring from one feeder to the other, so there is no interruption. All right. The other side of our other consideration in power quality is voltage magnitude. Previously we looked at continuity of service. Now we are talking about voltage magnitude. So there is a curve that is supplied by so-called CBMA. That stands for Computer and Business Equipment Manufacturers Association. Okay, Computer and Business Equipment Manufacturers Association. And they show that if voltage is in plus minus 10% range here, 90 to 110%, then there is no problem. Otherwise, you see this is the time scale over here. This is the magnitude. The voltage magnitude can be, so long as within this envelope, there is no problem. But if it's outside this envelope, then we have to do something. Okay, so that's what it's showing here. So one of the ways to keep this load voltage fairly constant, and here is the supply voltage. Let's use phasors over here. This is shown on a per phase basis, single phase basis. We can introduce this injected voltage across here. So if you can control this voltage which is injected, then even though this voltage may sag, by injecting some voltage in series, we can make up for the sag, so this load voltage essentially remains constant. Okay, and we can add this injected voltage to this, or if this voltage were to go above nominal value, then we can also should be able to subtract it from it in order to keep this load voltage constant. So there are systems like this on the market, and these are called dynamic voltage restorers, which inject voltage in series. At very large scale, we also have voltage regulating transformers, and transformer load tap changing is another option to keep the voltage supplied to loads constant. Another option is to use so-called StatCom. Okay, so StatComs are basically, so you have the utility here, you have some inductance, and these StatComs are basically a current source, leading or lagging. Okay, and this current source here can be controlled, and by controlling this current and the reactive power that is drawn or injected into this bus, we can control the magnitude at this bus here. Okay, making use of this impedance over here. Okay, so StatComs are also beginning to be used, and these are all solid-state devices. In the past and even now, switched capacitors are used. So by switching these capacitors in parallel over here, we can control the reactive power injected into this bus, and thereby control this, making use of this impedance, the voltage at this bus here, V bus. Okay. Now we go to the next topic in power quality, and that is making sure that the voltage waveform remains sinusoidal provided by the utility to loads. Okay, so in this section we will look at first, we can talk about the bad effects of distorted waveforms and how this distortion occurs in voltage and current waveforms. What is the displacement power factor, what is total harmonic distortion, and what is power factor when these currents are distorted. So we will look at all those. Just to mention, the deleterious effect of distortion is that when you have distorted currents being drawn, these distorted currents would cause unnecessary heating in transmission and distribution lines and transformers. So utilities do not like that because of unnecessary losses they are causing. They can overload capacitor banks, and they can cause some resonances in the system. So there are many reasons why we want to avoid distorted currents to be drawn from the utility, and they eventually end up distorting the voltage waveform here. And if this distorted voltage waveform is applied to, let's say, induction machines, then there will be additional losses in induction machines. So this is a bad thing all around, and we'll see what could be the cause of these distorted currents and how we can rectify them. All right. So, these distorted currents can be caused by electronic loads. And as we saw earlier, these electronic loads are supplied mostly by this voltage link system. And by and large, in these voltage link system, this front end, which is connected to the utility, is just a diode rectifier here converting this AC into DC, and that can cause very highly distorted currents to be drawn from the AC system. Or we could use a switch mode converter here, which then can correct this problem and draw essentially sinusoidal currents, and also at controllable power factor. So it can draw it as a leading current, lagging current, or at unity power factor from the utility. So, and these thyristor converters are used less and less these days, so we will not go into those. All right.